Large-scale heat pumps are a key technology for the energy transition. A heat source that can be used everywhere is ambient air. In this video, I show you how you can design a central air source heat pump for a district energy system using nPro. Hi and welcome to this nPro tutorial. I'm Marco, and in this video I explain how you can size and simulate a large-scale air source heat pump in nPro. Let's dive into it and see how that works.
On the start page of the tool, I click on the left-hand side on Energy Hub. Then we select a project template. I will use the coupled heat and cold supply. It's not really important what you choose here because you can modify the system in this view. We deactivate the heat recovery chiller. I activate a gas boiler, a natural gas boiler. So we have a system that covers heating and cooling demands. We have a heat storage, the air source heat pump, photovoltaic that can be used for the air source heat pump or can also be fed into the electricity grid. And here on the electricity grid parameters, I will change the supply price to 18 cents per kilowatt hour. And then we click on size technologies to see the optimal capacity of each technology. The photovoltaic is 318 kilowatt peak. The boiler has a capacity of around 200 kilowatt thermal. The air source heat pump 328 kilowatt, and the heat storage 917 kilowatt hours or 39 square cubic meters. We can change the capacities of the components if we want to. I will do this here a little bit. I will increase the boiler capacity and increase the photovoltaic area, and then click on simulate system operation. With the results of the simulation, we can then analyze how the operation of the system looks like. First, we have the energy overview here, the energy flows. The boiler covers a large proportion of the heat demand. The rest is covered by the air source heat pump. The cooling demand is completely covered with the heat pump, and most of the electricity demand of the air source heat pump is covered with the photovoltaic. If we want to analyze this a little bit further, then we can click on heat map. For example, we see first the electricity generation from PV, and that's the hour of the year plotted against the days of the year. So in summer, during noon and afternoon, we have the electricity generation. We can now click on the boiler and have a look when the boiler is operated. Especially in winter, it covers the heat demand, but we see some white areas here, and this indicates that the heat pump covers the heat demand also in winter when there's a lot of PV power. So we can have a look at the air source heat pump. This is the electricity demand, and let's have a look at the heating power. There we can see pretty well that it's only operated when there's also PV power, so when there's cheap electricity, and a little bit also during the very cold days. For example, in February, the air source heat pump supports the boiler. If we click on cooling power, then we see that the air source heat pump covers all the cooling loads, obviously, and leads to an electricity demand as well. If I click on summary, we can see the main KPIs of the system. For example, the electricity generation, 3/4 of the electricity demand are covered with the photovoltaic, and 1/4 is covered from the electricity grid. The heat generation, it's almost 50-50. The boiler covers 50% and the rest by the air source heat pump. And on the bottom we see the CO2 emissions and primary energy. The factors for the emissions as well as the primary energy factors can be adjusted in the settings of the optimization. If I click on economic results, we can see that the system is profitable, so revenues are higher than the costs. And we have a cash flow table here. We see that the net present value is positive, and a graph that indicates the same. We have the investment costs, we have energy costs, so from the electricity import and natural gas import, operation and maintenance costs. And here we have the revenues. The electricity feed in with 4 cents per kilowatt hour, but also the revenue for covering the heat and the cooling demand. Here we have a default value of 10 cents per kilowatt hour, but we could change this to, let's say, 8 cents per kilowatt hour, and then the calculation, the numbers as well as the net present value changes as we change the value here. We also have the possibility to download all the results as an Excel sheet, and there we also have the time series for every component, so the air source heat pump, the boiler, the electricity grid, and so on, and can do further analysis and create further plots.
If you have any questions or remarks about this video, feel free to leave a comment. If the video was helpful for you, please give us a like and subscribe to our channel. Thank you for your interest and see you next time.